Hi, class. Welcome to the next section, chapter 13.8. Today we'll talk about power series. Um, the remainder of the semester, the remainder of this chapter discusses power series and different types of power series. So this is our first introduction to power series, and then the remaining videos all cover different aspects of power series as well. So what is a power series? Power series has the form um, Cn times x to the n. Notice we start at 0, okay? The Cn is just a real value, a real number. It's a coefficient, okay? These look very similar to polynomials, right? So starting from 0, we have C naught, C0, x to the 0 power, which is just 1, so C0. For 1, n equals 1, we get C1, x to the first power, just x. N equals 2 is the second constant, or the third constant, I should say, or coefficient, x2 squared, right? Then c3x cubed, c4x to the fourth, et cetera, to infinity, right? So these have the form of the standard form of a polynomial when they look like this, okay? So say that Cn is equal to 1. So all of these coefficients are just the value 1. Then we don't have to write them anymore, right? Except for the first one. So we'll get the sum, just x to the nth power. And that'll just be 1 plus x squared, x cubed plus x to the fourth, et cetera, et cetera, et cetera. Okay. Because when I plug in 0, C naught is 1 because all of the Cn's are 1. Okay. This is a geometric series, if you can see here, right? And so it'll converge then when x is between -1 and 1. Okay, we'll talk about the relationship to that much more in depth later on, or as we go through this lesson, right? Um, it will diverge if x is outside of the value -1 to 1. Okay. A power series that is centered at the value of a or about a has the form uh, sum from n equals 0 to infinity, these coefficients from C naught, C1, C2, et cetera, x minus a to the nth power. Okay, so we're centered about this constant value a. So this might be a equals 4, for instance. So this will be x minus 4 to the nth power, some coefficient, right? And so all the different varying powers. So if we write this out as a series, it would look like this. Okay, so I'm looking at x values, but my center of focus is at the value of a. Okay, that's how you can interpret that. So let's look at a theorem. So for a given power series centered about a, there's really only three possibilities. Uh, One is that the series converges only when x is equal to a. The second possibility is that the series converges for all values of x. And the third is that there's a positive number r such that the series converges if the absolute value x minus a is less than r. Basically, what this is saying is that we are within a radius of r away from a. Okay, so just kind of think about what we're doing here, right? I haven't really shown you a graph yet. We're just really talking about what this is and convergence, right? Because we've been talking about series and what series are. But remember what I said, these things look like polynomials, okay? This is basically a polynomial. If I multiply this out, right, this will be a cubic that I can then add more terms together and it'll look different than this form here, right? Same with the cubed term and the fourth power term, et cetera, right? Each next term, approximate term, um, gives me a polynomial that I'll then add to lower degree polynomials when I'm centered about a, right? The general form of this. So once I add those all together, I'll get a polynomial of degree infinity, right? Very similar to this, but it'll have a different form, different coefficients that maybe don't follow a set pattern like this does. Maybe it does. Anyways, here we're talking about being centered at a, right? So if I'm interested in a function at a certain point, these things are going to look like polynomials that, now when we say converge, means that I'm only equal in value to my function of interest at A, I'm only equal to my function of interest represented by this function for all x in my function, so over the whole function. So my series gives me a good approximation everywhere for my function, or is equal to my function, or only within a certain radius around my point of interest. Okay, that's how we're going to, so I'm kind of jumping ahead a little bit, but that's how we're going to look at this. Okay, so it's going to converge if I'm inside of an interval around A, and diverge if I'm outside of an interval around A. R is called our radius of convergence, right? It's the radius of the interval where everything converges or is equal to some function of interest for me. In the first example, here converging only when I'm at my value, my radius of convergence is 0 because I don't converge anywhere in an interval outside of that value. I'm not equal in value at my function anywhere else. For the entire function, for the entirety of my function, those polynomials give me a good approximation. That means that my radius is infinite, right? This large polynomial that I have perfectly approximates my function if the radius of convergence is infinity, okay? So again, this is called interval of convergence, right? So if I'm a distance, some distance away from A, so a little x above, I'm sorry, R above and R below, then I am going to converge. Notice here that this is a strict inequality. Okay, so again, jumping ahead a little bit, I don't really know what's going to happen at R away. I just know that within a radius of R, I converge. I don't know what happens when I'm on the border of this radius. That's something that I would check on my own separately in order to get a true interval of convergence. Okay, so let's do an example. A very conceptual example here, right? So let's say that I have a series, it's Cn x to the n, so it's about the point x equals 0, right? So it's very nice when it's about 0 because it's not as convoluted, right? So it's just it just looks like a standard polynomial, right? It looks like this up here, right? So not C1x, it's this exact thing. Okay, so power series centered about 0. I know that this converges when x is at -3, and it diverges when x equals 5. Okay, so what can be said then about Cn2 to the n? So remember, this is centered at 0. So if I'm looking at x equals 2, I know it converges at -3, which means it'll converge at 3 also, or possibly not actually. But regardless, I know this is within 2 away from 0, because again, this is centered at 0, right? A is 0 here. This is centered at 0. So 2 is within a distance of 3 away. So I know that this has to converge. Okay. Here, I'm 3 away, but in the positive, right? I know that at -3, I converge. So what happens at +3? Since I don't know what my interval is, this could be one of these boundary points, right? At exactly 3 away, I converge, but that doesn't mean that on the other end of that, right, at +3, that I also converge. It's very possible that I don't converge there because it's on the boundary of my interval. So nothing can be said about the convergence of this series, okay, as compared to the previous. For Cn 4 to the n, 4 is more than 3 away from 0, so this is going to be, so nothing can be said here, okay? Because I only know that I diverge once I get to being 5 away or more. So 4, I can't say for certain exactly what happens here because I know I converge 3 away, but I don't know if I converge at 4 away or not, okay? So I know at 5 away, I am. So I can't say anything about 4. Okay, because it's an in between thing. Here, I'm 6 away from 0. I know that once I hit 5, a distance of 5 or more away, that I diverge. So this is going to diverge as well. Okay, so let's look at another example. We want to find the radius and interval of convergence. So here I have a series, -1 to the n, and x to the n. Now, before we go crazy about this, notice that this is an alternating series. The only way I can test for convergence for an alternating series is the alternating series test or the ratio test. The alternating series test, I don't know what's happening because of this value x. I have no idea what it does, right? Remember for the alternating series test, I need that each new term, absolute value wise, is less than the one previous. That could be possible here if this value of x is less than 1, in between 1 and -1, right? Because then I'd be multiplying this by small things, and the value will continue to get smaller. But looking at what this is right here, remember um, the alternating series test, I also have to look at the limit of the terms and determine whether or not it goes to 0. And I don't know if it does because I don't know what the value of x is here. I have no idea what it is. Okay, so I'm going to use the ratio test instead. What's nice about that is I'm either going to get less than 1, larger than 1, or equal to 1. So remember that I always, for the ratio test, I need whatever my limit is, I need it to be less than 1 in order for it to converge. So let's do the ratio test here. And so remember what we do is for the numerator, we put +1 everywhere. For the denominator, we leave it as is. This is absolute value. So just for posterity, I wrote everything here. But this whole -1 stuff completely goes away because it's absolute value. So I don't care if it alternates in sign because the ratio test has to do with absolute values. So again, right, when these cancels, -1 to the n, -1 to the n plus 1, when I subtract those, I get just one of these -1s. And again, it doesn't matter because it's absolute value, right? Here, I have n plus 1 times x over n. I'm looking at the limit as it goes to infinity. So the n's are what dominate here, and their coefficient is 1. So I just get x. Okay. Remember, for the ratio test, I need whatever my result is to be less than 1 in order to converge. So I need this converges when my value of x here is less than 1. Okay. So my radius of convergence then is just 1. Okay, because absolute value means x can be no more than 1 and no less than -1. So that radius from 0 to 1 is a radius of 1. Okay, so now I know when it converges and I know its radius or interval of convergence. So we also need to check the endpoints, right? What happens at 1? What happens at -1? Here it's pretty easy for us to tell, but we're going to go through this anyways, right? So I need to plug in 1 and -1 into my original value that I have here and then test the convergence. So for x equals 1, I get -1 to the n is my series. It's very easy to see that this just alternates positive, negative, positive, negative, positive, negatives, obviously, but the n just grows in value. So I bounce around 0, but I get bigger and bigger, right? So 1 above, 2 below, 3 above, 4 below, so forth and so forth and so forth, right? So I'm just bouncing away more and more towards infinity in both directions, which is divergent character, right? At x equals -1, the x value is the -1, which adds another one here, which is going to do the exact same thing, okay? So my interval of divergence is -1 to 1. The endpoint's not included, okay? Let's look at another example. For the next one, we have x to the 2n over n factorial. We're going to do the root test again. We always stick with the root test or the radius test because that test allows us to find the radius for convergence, right? So here I have x to the 2n over n factorial. I'm going to use the ratio test. So first I add 1 to all the n's, and then I multiply by the reciprocal of this, okay? Here, these factorials will cancel out. So this n factorial cancels out with the next term from this. So I'm left with just n plus 1 in the denominator. Here, Remember, put a parentheses, right? This will help you. That way you don't accidentally write 2n and then just plus 1. Because whatever this number for n is, I double it. So if I'm one above, one more in value, I then double it. I would not write 2n and then just plus 1. That'll give me a wrong value. So this is really 2n plus 2, okay? And so the 2n with the other 2n cancels, and I'm left with an x squared, okay? The n factorial and this factorial cancel, and I'm left with the n plus 1. Here, the limit for this is going to go to infinity, right? So this is going to go to 0, which means that the radius of convergence is infinity. It converges everywhere, right? The radius is infinity, and my interval is negative infinity to infinity. Let's look at our next example. So I have x minus 2 to the nth divided by n to the nth. This is very clear here. We should probably use the root test because both of these is to the power of n. So I'll take the nth root and the limit of that as n goes to infinity. The n's cancel, so I get x minus 2 over n. Okay, n goes to infinity. This whole thing goes to 0. So again, I have a radius of infinity, and my interval is from negative infinity to infinity. For d, I have 2x minus 1 to the nth, 5n to the square root of n. I would use the root test here as well because I have powers of n, top and bottom. Okay, this is going to give me 2x minus 1 on top. This is going to give me just a 5. This is n to the 1/2. So this will be 1 over 2n, okay, for the power. So when I go to infinity, we saw already that this goes to 0 faster than n does. So the denominator will just be 1 times 5. So this will be 2/5 times x minus 1. Okay. And remember, this is only going to converge if it's less than, or I'm sorry, not equal to, if it's less than 1. Okay. Because it's the root test. I need my result, my limit in this case, because x is not n, right? So I don't care about what x, I do care about what x is. I'm about to do that right now. But when I'm taking the limit, I don't because I'm worried about n, right? So I need this to be less than 1 because that's the condition for convergence from the root test. So I set it less than 1, okay? And I'm going to get rid of this 5 by multiplying by 5 on both sides, okay? And here, I would like for it to come back here, look something like this. X minus a, right? X minus a less than a radius, right? So that's my goal. I'm trying to get x alone and then plus or minus some value, okay? So first thing first was I got rid of the 5 by multiplying it out. Now I have 2x minus 1. I want x alone equals a number. We'll have it multiplied by 2. So what's the opposite of multiplying by 2? Dividing by 2. So I'm going to pull out a factor of 1/2 out of everything. Okay. So if I take this, I'll have, if I factored out a 2, I would have x minus 1. And then to get rid of that 2 that was here, I'd have to divide it on both sides. So that's why this is a 5/2. So now I have x minus a number, right? Even if it's a fraction, that's fine, is less than some value. So in order now to figure out what this radius is, I add 1/2 to this, and then, I do my signs, I switch the sign, and I make this negative, and I subtract the 1/2, okay? So my radius of convergence is 5/2, centered at 1/2, okay? So I'm convergent between, so if I separate this into its two pieces, right, negative 1/2, less than 5/2, and then the opposite of that, which is switching the sign and making this negative, and then I just add 1/2 to both sides. That'll give me less than 3, but more than -2. So I know I'm convergent in between this interval. However, I don't know what happens at -2, and I don't know what happens at 3, right? On the bounds of this interval of convergence. But I didn't know for a fact that within this interval, I do converge. Okay, so I got to look at the endpoints as well to get a full picture. So if I plug in 3, the numerator becomes 6 minus 5, or sorry, 6 minus 1, which is 5n. And then this stays the same, because remember, I'm plugging this in for x, not n. I know it can be confusing when you have too many things. We've been looking at n a lot, but your whole lives you've been looking at x. So it's very easy to get these confused and then accidentally plug in 3 everywhere, right, for x and n. So be very clear that this is for x, not for n, okay? So when I plug in 3 for x, I now have a series that I can try to determine convergence. Again, the root test looks like the thing to do. I'll get something very, very similar to what I'm getting here, except that I don't have to worry about this 2x minus 1. This 2x minus 1 will then basically just be replaced with 5. Okay, so actually applying the root test, we're going to get the same thing. Okay, so I pretty much just jumped, right, because this will be 5 to the n over 5n. So before I even, you can see it canceled before I even apply the test. So we can see here that this is actually a divergent p-series, right? So we can go ahead and just go with the p-series and talk about it being divergent, right? Because it's less than 1. So at the endpoint of 3, at the further endpoint, right, at the largest value, it diverges. So looking at -2, same thing, we're going to take -2 and plug it in everywhere. So this is going to be a -5 to the n. So it turns now into an alternating series. So I can't just cancel it out. But here, the root test would be appropriate. Okay. Oh, well, I guess I can't pull out the 5 and cancel that way. Oops. So, all right, these still go together. So I'm looking at an alternating p-series, right? So we saw before that if it's alternating, that it can be conditionally convergent, right? So it's possible that this converges. So we're going to do we're looking at the next value compared to the previous value, right? So we're applying the alternate series test. You could go ahead and try to do ratio test on that if you want to, except we said that p-series style things don't work so well. We normally get inconclusive results. So we are going to apply the alternating series test. This is smaller in value than this, right? Larger on the bottom than this is. So it is decreasing in value as we go. Okay. And if I look at the limit, so 1 over n to the 1/2 is the square root of n. So as this gets bigger, the whole thing gets smaller. So the limit does go to 0. So this is convergent. Okay. So therefore, my radius is 5 over 2, which I already knew. And my interval converges on the endpoint of -2, but diverges on the endpoint of 3. And it's centered at, what was our center at? At 1/2. Okay, we're centered at 1/2, negative at 1/2. And there you go, and a radius of 5/2. Okay. So on the next video, we're going to talk about power series and how we use them to approximate a function. So I know I hinted at it in this video. We talked about it very generally, without any pictures or anything. So we're going to really talk about that in this next section. Really, really, in the section after that is really when we get into um, using these series to approximate power series to approximate functions. Okay. See you guys on the next video.